Hello, I'd like to explain the characterization process for crystal units and ICs. Do you often have concerns that your final product may have trouble initiating startup protocols, establishing connections, or improperly operating? This may originate from a stop in oscillation or frequency shift in the oscillation circuit. When we use oscillation circuits in the wrong way, this causes a problem. Proper design of the oscillation circuit is needed to avoid this kind of problem and create stability. Murata has lots of IC characterization experience for automotive and industrial applications and would like to introduce our IC and crystal characterization process. To begin, I'd like to explain the role of oscillation circuit components. This is a general oscillation circuit. It has an IC, which has an internal inverter circuit, a crystal unit, feedback resistor, damping resistor, and external load capacitors, C1 and C2. To find the most suitable circuit constants, we must first evaluate the oscillation circuit. I'd like to begin by explaining the role of the feedback resistor. The feedback resistor is implemented to create a feedback circuit in the oscillation circuit. Recently, many ICs have begun utilizing internal feedback resistors. Because of this, an external feedback resistor is not typically required. If a feedback resistor is needed, a 1 megaohm resistor is generally used. Next, the role of the damping resistor, RD. The damping resistor is connected in series with the crystal unit to control the drive level and to avoid irregular oscillation. A damping resistor is not always needed depending on the oscillation characteristics. Sometimes it is also used to avoid EMI/EMC noise issues. Now, the role of the external capacitors C1 and C2. External capacitors are connected between the input and ground as well as the output and ground to control the oscillation frequency. Some ICs have internal load capacitors that can be adjusted through programming. Load capacitors must be accurately selected, not too small, not too large. They are an important part that directly influences the negative resistance and the oscillation frequency. To select the best circuit constants, we evaluate 3 oscillation parameters: the oscillation margin, drive level, and frequency correlation. The oscillation margin provides the limit at which oscillation stops. This margin is indicated by a ratio based on the equivalent series resistance, or ESR, specification of the crystal unit. Drive level indicates the power consumption of the crystal unit while oscillation is underway. Frequency correlation is the difference between the frequency measured from Murata's standard circuit and the user's circuit. The oscillation margin and the drive level are the key parameters to affect stable oscillation. Drive level and frequency correlation impact the oscillation stability. We select the optimal circuit constants by confirming these 3 parameters. More webinar information is available on how to measure each parameter. If you have any questions or concerns about IC and crystal unit characterization, please contact Murata. Thank you for watching.